Welcome. A CRAY machine description. Why would you want to do that? The CRAY architecture was designed in the first half of the 1970s, therefore predates GCC by at least a decade. So we know for sure that in the design of this architecture, GCC didn't play a role, say, to having a free compiler. And although it didn't predate the C language, strictly speaking, because that was also developed in the early 70s, it wasn't made to run C programs easy, as I will show shortly. In fact, its main purpose was to run machines that do nuclear bomb simulations and weather forecasting models, all written in Fortran. So an open question for me was, how well can GCC work on such an architecture? And as a reminder, don't try this at home, because CRAYs are machines that still use Freon as cooling material, and that's inhibited these days. They're also very expensive. No, my garage is not large enough for that, I'm afraid. Although they weren't physically large machines. The CRAY architecture is a typical, some would say, archetypical RISC load store design. So that means that you have registers and you load values from memory in a register. You compute things only in the registers, and after that you store the value of a register in memory. And register-to-register operations have three operands. Addresses point to 64 bits words in memory. And that's an interesting thing, of course, because we are all used to current architectures that store 8-bit characters or bytes into memory. And one of the first things that this talk assumes is that we can set bits per unit to 64 in a machine description. We'll see if that will work. I haven't tried it yet. This talk is just to see if someone can come up with a reason why this architecture can't be done with GCC. It has 8 computational registers with 64 bits per register, and they contain either an integer or a floating point number. And it has 8 address registers of 24 bits. Of course, in those times, memory was very expensive, so 24 bits could already address 16 million words or 128 megabytes. Doesn't sound like much these days, but at that time that was the most expensive and also the most energetically expensive part of the machine. Both register sets have a 64-member shadow register file. So you have 64 T registers where you can store an S register and 64 B registers where you can store an A register. This will be a question further down the road for the register allocator. In addition, it was a vector machine, even in these earliest times. It has 8 64-element, 64-bit vector registers. They called V. And both the S and the A registers are loaded from and stored to memory using the address containing an A register plus a 20-bit offset. And A0 was special in the sense that if you use that register, only the offset was used. So it was equivalent to A0 being 0. CRAY does not have a floating point division instruction. In that sense, it's also special because CRAY thought that if you just computed the reciprocal of the floating point divider and used multiplication, that was sufficient for the accuracy. And in the manual, for which I have a pointer in this in these slides, it is explained how you correct, say, that approximation to the division. Needless to say, the CRAY also predates, of course, the IEEE 754 standard of floating point numbers, because that was dated also from somewhere in the middle of the 1980s. Now, why or what are the challenges if you want to use GCC to try to model such a machine? And in fact, these challenges already started when I first had to use one of these. One of my previous employers bought a 4-processor CRAY YMP running the Unicos operating system. That was a variant of the then widely used Unix before Linux ever existed. And because it was acquired to be used in as a national academic supercomputer in the Netherlands, it should have had a very good connection to the internet in the Netherlands. And that was one of the problems I and my colleagues had to address, whether this connection was indeed good enough, and if every university in the Netherlands could reach the machine, and vice versa, if from the machine every university could be reached. Well, in that time there was only one IP application that you can use to figure that out, and that was called traceroute. I mean, it still exists, but it's not that useful anymore these days. But other than nowadays, when you have Linux distributions, traceroute wasn't just part of the Unicos operating system of the machine. So I had to download it from somewhere from the internet, the source code, and try to get it working with the internet facilities of the machine. But that's a real problem, because if you have the old IP version 4 internet protocol that consists of 32-bit addresses and lots of stuff inside a small packet. Now try to figure out how you use that in a C program that in fact only has 64-bit ints. That's quite a challenge. I could figure out how it worked by looking at all these header files of the IP implementation on Unicos, but it was very daunting. I think I dropped this project 3 times before I actually finished it. So for fun, I tried to figure out what their C compiler would do with this code. It's a simple copy of a character string, a 0 terminated character string to another location. And it turned out that character pointers were implemented on this machine, not in the address registers, but in the full integer registers in 2 parts. One part was the address of the word where the character was stored, and the other part was the offset. And this must be one of the things that probably is a large problem if you want to do this in GCC, because I don't think this is easily possible. And well, you can see that it, or you can't see because I forgot to bring the actual generated code, but it's not hard to think how this was working out in that loop that I show you here, because you have this address with two components, two of them, the S and the D address. And in the loop, the things have to be shifted and masked out. And then the individual characters also have to be shifted and masked out. And in the end, in the total, I counted 80 instructions to do this, which on a normal machine takes a couple of instructions. So the question is, can GCC do this? Could SLP help us with this by storing at least 8 characters in a row in a register or a memory word? And how would that work? So this has no answer yet. Now another challenge is, and that might not be that much of a challenge, that the 8 S registers and the 8 A registers have 64 member shadow files, shadow register files, where you can copy their contents to. Now it would be nice, of course, if the register allocator would know how to copy these registers to these shadow registers in case it needed the main register for something else. So what we call spilling. And perhaps this is possible. I don't know yet. I have to ask the person who actually wrote the LRA register allocator if this can be done. But that's a second challenge.
Actually, it was implemented for x86-64 spilling integer registers to X registers.
Ah, okay.
It was switched off because it did not give performance.
Okay.
So there is some mechanism, I guess. But the problem is not local register allocator, the problem is global register allocator. You need to, because we use coloring already, and there is no priority for shadows or what order of pseudo to be hard raised. What pseudo is more important. But we can add something to treat this shadow register as initial stack source. But it needs some modification in global register.
Okay.
And we need to describe machine as no shadow register on the area register. So spilling will be done in global register located in the shadow registers. And LRA will do reload if we need to do something besides store and load. Something like arithmetic.
Okay.
So I guess the changes for global register locator will be like 200 lines.
Hmm.
For LRA, you can't get more.
Okay. Well, interesting to know.
I apologize, we are running out of time. There are 3 more lightning talks.
Yeah. Can I have the last challenge? This one? Yeah.
Please.
Branching. The memory is 64-bit wide, so you would expect that the branch goes to a 64-bit address in the memory. But the CRAY is special in this case that it knows that instructions are either 16-bit or 32-bit wide parcels, and it jumps to a parcel in the sense that it takes the address of the word and then the number of the parcel. And the difficult thing is, of course, that you don't want to jump inside a 2-parcel instruction, because that would wreak havoc. Okay, now this is very quick. There's a pointer to the CRAY architecture manual over here. And yeah, vector registers shouldn't be problematic. There are more than in normal CPUs, but they're very, yeah, they're not special for some, right? Okay, thank you.
Thank you.